Hi guys, so this time we're talking about the variation of Kp with temperature. This is section 6.9. So we saw back in section 6.7 that natural log of Kp is equal to negative delta G of reaction standard conditions over RT. We also know delta G is equal to delta H minus T delta S. So if we substitute this for delta G up here, we can write this as natural log of Kp is negative delta H of reaction over RT minus delta S over R. See this T here canceled with one of these T's right here. Now we can differentiate this to give us the dependence on temperature. If we take how ln of Kp changes with temperature, that's dln Kp dt. So if we take differential on both sides, if delta S does not depend upon temperature, at least not significantly, then this term has no temperature dependence, and d, that term with respect to T, is 0. It goes away. So we just get this term here, the derivative of that with respect to temperature. So we have dln Kp dt equals d that dt right here. And that's easy, okay? Again, once more, assuming that delta H does not change with temperature over the temperature range of interest that we're talking about, then we can ignore the temperature dependence of delta H of reaction, and the derivative is easy. It's just negative 1 over T squared. Negatives cancel. We get this. Nice equation. This is from your textbook. This is shown for two important reactions: the synthesis of ammonia, hydrogen and nitrogen combining to make ammonia gas, and coal gasification, reacting steam with coal, solid carbon, to make carbon monoxide and hydrogen gas. Both important reactions. And we see here, okay, they're plotting delta S versus T, delta H versus T, delta G over T versus T, and delta H over T versus T. So we can see here, this is the green line and the blue line, that delta H and delta S don't change much with temperature. That's good. So our assumptions were good. Now, we know that enthalpy probably changes with temperature, and certainly entropy changes with temperature, but this is the delta H and the delta S of the reaction. And so as long as the reactants and the products are similar in their entropies, the delta S is not going to be, and delta H likewise will not be significant. For this reaction here, we're making 2 moles of gaseous products from 4 moles of gaseous reactants, so as we would expect, delta S is negative. Over here for the coal gasification, likewise, delta S and delta H we see do not depend very much upon temperature. The change in entropy and change in enthalpy is not very different. Also, delta S is positive because we're making 2 moles of gas from 1 mole of gas. The solid doesn't really contribute much. So while delta H doesn't change much, notice delta H over T does, okay? And that's important because that's part of our expression. Okay. So here's what we know. dln Kp dt equals delta H over RT squared. So we can look up values for delta H, delta G if we want to use that form of the expression, Kp in tables. But here's the thing. In all those tables, they're almost always at 298.15 Kelvin. If we need to, which usually we would actually, because temperature is almost never exactly 25 Celsius, find Kp at a temperature other than 298.15 Kelvin, all we do is integrate. So multiply through by dt, integrate d ln Kp, and then d delta H over RT squared dt from 298.15 to whatever temperature we care about. And once more, if delta H of reaction does not change significantly over the temperature range from 298.15 to whatever we're going to, then we can assume this is constant and we can ignore the temperature dependence of delta H, pull it out front of the integral, and it becomes a real easy integral. So integral of d ln kp is just ln of kp at the final temperature minus ln kp of the initial, which is 298.15. The integral of this dt is just delta h over r. Pulls out front, we get 1 over... okay, so I did a little funny stuff here with the signs. Okay, it's final minus initial. But the integral gave us a negative sign. I brought that inside and made it the initial minus the final. So check that out, but it works out. Rearranging this, solving for what we really want to know, natural log of Kp at some temperature is equal to natural log of Kp at 298.15. Usually we look this up, we can calculate it too, plus delta H over R times 1 over 298.15 minus 1 over the final temperature. So we're going to use that in just a second, guys, but here's what we can say qualitatively, that what determines how Kp changes with temperature is the delta H. That's the delta H over T term. If delta H is less than 0, it's negative, then Kp decreases with increasing temperature. If it's greater than 0, Kp increases with increasing temperature. Let's look over here, back here. Delta H is negative. Delta H over T, delta G over T, which is natural log of Kt, decreases with temperature. Here, delta H is positive, it's up here, so they increase with temperature. And the delta S of the reaction has little effect on the Kp's dependence on temperature, how it depends on temperature. So we're not going to have to worry about it. So here's an example. We want to calculate Kp at 759 Kelvin and 2214 Kelvin with pressure equal to 0.059 bar. For this equation that we looked at in the last section, the dissociation of the chlorine molecule into atomic chlorine, and also calculate the degree of dissociation, beta. We saw these before, at these temperatures and this pressure. So starting out, taking the integrated form, natural log of Kp at the temperature we want, is equal to natural log of Kp at 298.15 plus delta H over R, 1 over 298.15 minus 1 over the temperature. We're not given Kp, but we can, I guess we could look it up, or if I had 298.15 or calculate it, because it's just equal to negative delta G over RT. This is a real easy calculation, because if you go to the back of your textbook, delta G of reaction is just going to be the delta G of formation of the products times 2 minus delta G of formation of the reactant. But the delta G of formation of chlorine, that's its elemental form, is 0. So it's just 2 times delta G of formation of atomic gaseous chlorine, which is that number. And we get this for delta G of reaction. We are also, guys, going to need delta H. So same way, delta H of formation of the products times 2 minus delta H of formation of the reactant. Also, delta H of formation of elemental chlorine 0. So we just get 2 times the delta H of formation of atomic gaseous chlorine, which is this number. We get that. All right, so we have these numbers here. So we're going to be able to get natural log of Kp, thus Kp, at 298.15 if we need it, and also delta H, so we can plug in. So let's do that. So getting natural log of Kp at 298.15. We calculated delta H of reaction, negative here, R. I have R as 0.008314 because it's kilojoules per Kelvin mole. 298.15. We get this number here. It's, oops, I don't want to do that. It's dimensionless because natural log of a number has no dimensions. So now to get the natural log of Kp at 759, plug this number here, there, for the first term, plus our delta H over R, 1 over T, 298.15 minus 1 over T final. Check my math, guys, please, but I got a negative 25.858. And so to get Kp, take e to that, which gives us 5.9 times 10 to the minus 12. And then we're going to bump up the temperature to 2214 Kelvin. Same thing, same natural log of Kp at 298.15 is this term. delta H, R, T final 298.15. This is the only thing that changes, but it changes it significantly. So we get natural log of Kp at 2214 is this number here. Taking e to that, we get 0.55267. So what's that? 11 orders of magnitude larger at a higher temperature. So which kind of makes sense. But let's go over here and calculate the degree of dissociation at the two temperatures. We derived this relationship for the degree of dissociation back in the last section for this particular reaction. Remember, this only applies, this equation only applies to this particular reaction, but or one like it. But that's what we're doing, so cool. Plugging in at what is it, 759 Kelvin, we got this Kp. Pressure is that's pressure. Kp there, and I got like about 5 times 10 to the minus 6 for the degree of dissociation. Not very dissociated, so that means that it's mostly the chlorine molecule, not there are very few atomic chlorine atoms. And then doing the same thing for 2214 Kelvin, we get a degree of dissociation that's like, it's like 84% dissociated, so it's a lot more dissociated at that higher temperature. And that's true for any endothermic reaction. As you increase the temperature, you increase the degree of dissociation.